My name is Tim Dwyer. I'm Chair of the CIBSE ASHRAE Group and Teaching Fellow at University College London. I'm chairing the webinar. The title of this webinar is Data Center Energy Efficiency: Who, What, Why, When, Where and How. We're fortunate in having two world-class speakers. Don Beaty of DLB Associates speaking live from the USA, and Paul Finch of Digital Realty live from London. Don Beaty has over 30 years experience in consulting engineering and founded DLB Associates Consulting Engineer in 1980. He's a licensed professional engineer in over 40 states, as well as having international licenses. Don co-founded and was the first chair of ASHRAE TC 9.9, Mission Critical Facilities, Data Centers, Technology Spaces and Electronic Equipment, and currently serves as its publications chair. He's also a frequent keynote speaker on behalf of ASHRAE TC 9.9 for the data center industry, having presented over 100 times in more than 25 countries on various data center-centric topics. He will be followed this evening by Paul Finch, Senior Director of Digital Realty, a real estate investment trust. Paul is a senior engineering and construction executive and has extensive global experience across the full spectrum of development management and complex engineering-led capital projects and operations, with a particular focus on the design, construction and operation of data centers, technical real estate and high dependency mission critical assets and infrastructure projects across the telecommunications, technology and banking and financial services sectors. He's a voting committee board member of ASHRAE TC 9.9. So without further ado, let's go to our first speaker, and this is Don Beaty of DLB Associates. So across to you, Don.
So this is me, and the second speaker will be Paul. So today we're going to talk about some data center basics, some key trends within the data center industry, energy standards and regulations, measurement of data center energy, best practices for efficient operation, innovative concepts and solutions, and then further reading. So first of all, we're assuming that some of you are not experienced with data centers. So let's just go ahead and start by saying that a regular commercial office building, that building, the amount of power it draws per square meter or square foot is order of magnitude 1/10 that of a data center. The data center is 10 times it. And then on the energy side, since the data center is 7/24 versus a business hours or something along those lines, so you have 3 times the amount of time per year to really work on a return on investment because it's under load all during those times. So really a totally different kind of project type than most others. So here gives you an example, fancy data center with all the fancy coloring here. You see here we have these infrastructure that goes along like unistrut to go and suspend various things, like here's a cable tray and another cable tray and so forth. And one of the things therefore that's difficult in a data center is this is like a roadblock to the cooling. Whether you have the return up here or you have the supply up there, and then this colored area here, we would call that a data hall. And here, these are just rows and rows and rows and rows of racks or cabinets. And over here on this side, it's the same thing, but in a colo facility, there could easily be it organized into cages. So a private cage to be rented out, and therefore it would have 1 rack, 2 racks, 5 racks, whatever. An interesting thing looking at this particular schematic here is of a fairly low density load here compared to a lot of data centers. And look, even with that, if we look at the overall footprint, the amount of space that's consumed by the mechanical electrical. order of magnitude about 50% of the size of the data hall itself. There are plenty of data centers where it's a 1-to-1 ratio, so really a significant kind of thing. So we've got the heat rejection here and the pump room and the electrical gear and the UPS and these generators here, and then these computer room air conditioning units and so forth. One of the interesting things from a mechanical engineering perspective is because it's typically 10 times the concentration of power of an office building or things along those lines, is it's very easy for this area here to create its own microclimate and therefore get short-circuiting of air going different kinds of ways, and so that needs to be looked into on every project. So here we go. We look at that commercial, conventional building, and who are the occupants? The occupants are humans, and right up here we have it written that one of the ways that in traditional buildings they call things FF&E, fixtures, furnishings, and equipment, and therefore in a space like this, this is the fixtures, furnishings, and equipment. And it's important to differentiate this, to understand this, because people think the occupants in a data center are the racks, the servers, and that's not it. That's the FF&E. Where are the occupants? They cannot be seen. They are software. And so the problem we have over in this area as far as transient occupancy is trivial compared to the speed with which the occupancy can change in a data center. Anytime there's a software upgrade, a new piece of software added, any sort of change in need, it's not dependent on anything else. The software can go ahead and start to consume more capacity. And so this really ends up creating interesting things for us regarding how to go about designing a data center from a mechanical engineering perspective, because the range of change and the rate of change, speed of change, can be so much more significant than in an office building. For example, you could go from a load of 2% up to 95% in a minute. And then you could go back down that same sort of way if it was a batch process or other types of things like that. So a lot more thought needs to be given to part load conditions, bin hours associated with occupancy, bin hours associated with climate, all those sorts of things all need to be considered. This shows you an example of some of the equipment. So down here we have examples of racks, different ones, and got all these different little computers here called servers. And so these show a cabinet kind of arrangement. And here shows just an open frame arrangement. And we have in a data center an interesting thing in that we have this type, and see here's 1, 2, 3, 4 posts. And this one there's 4 posts, this one there's only 2 posts. So in plan view, if we've got a post here and a post here, and we have a rack, a server here like that, and then we have a post, another one, we could see how we could get all kinds of short-circuiting going on. And so that's an important thing to keep in mind. Typically, the 2-post racks have to do with the network and the telecommunication side of things. Here shows back in the day, the tower type of server, and then here's the 1U server. That's the size of a pizza box, order of magnitude. 1U, that's a rack unit, and a given rack here, you see these little pieces here like that. There are typically 42 U's, 42 rack units. It means a 1U server, you could put as many as 42 in a rack. And then, so these were what we had back in the day, a tower type of server or a tower type of computer we would have at home, and that changed to this. And so notice the difference in the form factor, and then it switched to a blade where these are each inserted vertically versus this type where they're typically inserted horizontally. So a lot of variation can happen as it relates to the form factor and shapes and so forth. Here we look at, sometimes we call this a stack, a hardware and software stack. So here we have that hardware, and that hardware again is F&E. And then we have the system software. So system software would be things such as the operating system. And then we have application software, and then we have the user. And so all these things come into play, and this doesn't change as much as this, and this changes all the time. They're always receiving new apps and new needs and interests that change our demand. So now we'll go to the key trends in the data center industry. So this is a chart that's produced by the Thermal Management Consortium through the Uptime Institute in 2000, and then ASHRAE started publishing it in 2005. And here on the x-axis is the year the product was announced, and here on the y-axis is the kW per rack in density. You can see here around this point is when it started really rising. This particular one here happens to be for compute servers, and then this was for storage servers. And as we've gone along, we've had to split up into more and more curves because there's just too much variation in the load growth depending on the type of server it is. Here we see a particular manufacturer, and we go ahead and this really is an interesting thing. It's a 4U, so it's the height of 4 pizza boxes, and there are 4 processors in it. And quite often you can configure computers in a lot of different ways. And so in this case here, we configured from 2007 to 2011 the same product. There are different generations, generation 1 through generation 4. And what we did was we held as a constant the IT performance. So in year 1 is 100%, and year 4 was 100%. So we did not try to improve on performance, but hold that solid so we could see what else would happen. So on the IT power per rack, if the base year generation 1 was 100%, we look at generation 4 and it went to 119% or 19% change. So the IT power per rack went up by 19%. The rack count, we went from 60, here's generation 1. If you add these up, 1, 2, 3, 4, on down the line, there are 60 racks right here, and then we've got cooling equipment here. So in generation 1, we had 60 racks. We went to generation 2, and we had this amount of racks. We went to generation 4, and we had 8 racks. So we could do the same compute performance, 100%, with only 8 racks versus 60 racks. So a reduction in the number of racks by 87%. But of course, as we're doing this, we get a lot more performance, less racks, but what's happening here is this is becoming more and more concentrated. Now, if we go back up here for a minute to the rack again, we look and we see here that order of magnitude, a rack is the size of a refrigerator. A refrigerator isn't as tall, but it's kind of about the same sort of footprint. Now, it turns out when we go and we look at this curve right here, what we see is that there are racks now that are available at the up to 60 kW a rack, really significant amounts. And so what's important about that is to go back to that refrigerator right here and imagine trying to cool a refrigerator whereby it's equivalent of 6 fireplaces. 10 kW is equivalent to 1 fireplace. So 60 kW would be 6 fireplaces. So imagine that kind of concentration of heat and the challenge associated with that. So that is why these trend charts are so important, because they help us to predict out what the trends will be. And so this table is showing us that we're going from the 60 to the 8, or an 87% reduction in the rack count. The power, the total IT power, 18%, down to 82% there. Space required down, on down the line. And so what happens is the same work that's done here is here, but what people tend to do is they want to go ahead and fill this up anyway, and just builds more and more stuff here, and it all adds up. And further, what happens is they don't hold this to 100%. They want this to be as high as possible. So that might be 150% or 200%. And then all these other numbers here go up as well. Here's our psychrometric chart. And before the committee started, we were, the industry thought cooler was better. And it was very common to have 20 degrees C, plus or minus a half a degree, or something along those lines. Maybe it's 1 degree. And so if we look here at the psych chart, we've gone ahead and published this, and all the IT manufacturers agree with it. They're all on the committee. And even for legacy equipment in this A1 class and A2 class, it applies to legacy equipment, which is what it's saying right here. It applies to legacy equipment. And what this is showing is, what's the point? It's not about a point. So if we look at the 20 degrees here and had that small band there, that's nothing. This whole recommended area, we can be anywhere we want in this envelope. And we define the rate of change in this envelope as well. And all the equipment that the manufacturers make, they test it to the recommended level, which is a reliability and energy performance statement, and then they also test it to whatever allowable rating that piece of equipment is. Of course, the larger the envelope, A1, A2, A3, the bigger the opportunity for using an economizer and the amount of economizer hours. Allowable does not impact the warranty. If it's a piece of equipment that's rated for A4, then working mostly in the recommended range, but allowing excursions out into A4, anywhere we want to go, is perfectly fine to do. This kind of shows us a little bit about a volume server. So volume servers, there's no clear definition in the industry of a volume server, but order of magnitude, a volume server is 90% or more of all servers that are sold. Typically, it's all servers other than a custom box, they would call it. So 1U, 2U, 4U, blade servers, all those things are all volume servers. So where we are currently, the power demand growth is 2 to 6% compounded annual growth rate. And so therefore in 3 years, it'll be 5 to 20%, and in 5 years, it'll be 10 to 30%. If we look at the performance growth though, we're going at a much faster rate. And this is where people get confused. They think that the improvement in energy performance on the servers means that our density is not going up. But we need more and more compute capacity because we just keep on coming up with more and more opportunities to use it in a productive way. This shows, this is the now no longer a trend chart. This is one we've published recently, and it's showing what the change is from 2010 to 15 to 2020. It's showing that depends on the rack height, the server height in rack units, the number of sockets, 1, 2, or 4, and so forth. And these are blade servers. And what this is showing is, here's the heat load, actual heat load. If it's fully loaded, that's this is the amount they'll draw. So it went from 255 for a 1U, 1 socket, to 330 in 2020. And again, our track record is really good. on predicting what it will be. We predicted in 2005 to 2010 that all came true. So now, if we look at this per chassis, 2010, 15, and 20, if we want to multiply by 42U, if it's 1U, because a rack is 42U, here's where we get the KW, 10 KW, 12, and 13. So what we see here is if we compare 2010 to 2020, it's a 29% increase. What's so powerful about this chart, so powerful, is the fact that it shows that it depends on the type of server as to the growth rate, and the growth rate goes from 29% at a low, 20% as a low, to 67% as a high. So we need to look at the individual ones in order to make that work. Here we're showing how to take that trend information and apply it. So if we look on that 2010, 2015, and 2020, and we see here 600 for 2010, we see that's what it is here, this one socket. 600, 735, and 870. And that's maximum configured, full loaded system. So if you have a system that's not fully loaded, for whatever reason, you could go and you could look at today's server, where one in 2010, and if yours was, for that same product, was 300 watts, then you could work out a ratio of 300 to 600 and be 0.5, and that means you could take each one of these numbers here, there's a projection, and multiply times 0.5 and get a projection. And this is important to us because a lifetime for typical IT equipment is 3 to 5 years. And in ASHRAE standards and CIBSE standards, the lifetime for mechanical equipment is 8 to 25 years, depending on the type of equipment. So we're going to see 3 to 5 lifetimes of IT equipment in our one cooling system. So therefore, it's important for us to project out what it might be. About that one, so here's ASHRAE 90.1 is a model energy standard. And what's important here, you see these different categories. We see these categories, and it doesn't talk about data centers. And so prior to 2013, 90.1 considered data centers to be a commercial process, and they were excluded. And so now they're added in there. And so that's a change, and so now we need to consider that. And 90.1 is adopted by a number of countries around the world. ASHRAE Standard 127, the purpose, the scope, definitions, so forth, this has to do with unitary air conditioning equipment. And this is an important standard for us because the equipment that's used for a data center has a totally different sensible heat ratio. And so that's where this standard becomes really important, and it's good to reference it if you're working on a data center. Here's our thermal guidelines book. We're in the 3rd edition, and that's where we saw that psychometric chart, and it has all kinds of different things in there as relates to patterns and heat and airflow reporting, etc. And now finally, Paul's up.
Thanks, Tom. It was. I'm glad you did that piece on the energy standards. They are very US centric, but I guess one of the things it's worth noting is the data center industry as a whole is fairly unique in terms of the global standards that people refer to, and so that was an important piece. So thanks for that, Don. Don's provided some basics around the data center, key trends, and energy standards and regulations. And now what I'm just going to start to present is some background on measurement of data center energy. I've just lost the presentation on my screen. It's back. Okay, there must be a glitch. The common term used and metric used for data center energy efficiency is PUE, power usage effectiveness. It's considered to be the industry preferred metric for measuring infrastructure energy efficiency for data centers. There is also a metric termed partial power usage effectiveness, which was originally created to avoid what was a misuse to some extent of PUE when only part of the total power was being considered. And I can explain a little more about that in some of the examples I'm going to present shortly. PUE was defined by originally defined by the Green Grid back in 2007, and fundamentally it was developed with the objective being to improve the resource efficiency of IT and data centers as a whole. PUE is an annualized metric, so we consider kilowatt hours or megawatt hours rather than kilowatts. So the measurements are taken over 8760 hours per year. PUE can never be less than 1, the 1 being the IT load. PUE does not receive credit for waste heat repurposes. For example, if we were to take waste heat away from the data center and use it to perhaps support some heating or preheating to an adjacent office area, that wouldn't be considered to form part of the PUE metric calculation. However, there is an alternative metric, EUE, which I don't plan to go into any detail today, which does take that into consideration. As I said, PUE is being globally accepted and is widely used across the data center industry as a whole. It's becoming increasingly important as the data center industry focuses on improvements in energy. And as an example, from a commercial perspective, PUE caps are now becoming commonplace in lease agreements, whereby we're developing a data center, we're looking to lease the space, and there'll be PUE caps introduced within the lease to ensure that the facility works within a certain threshold, and if the owner was to deviate or landlord was to deviate beyond that threshold, then there would be some financial consequences associated with it. So the measurement of data center energy, PUE and PUE, partial PUE, sorry, is fairly straightforward. So PUE is the total facility energy divided by the IT equipment energy. The total facility energy would include UPS switchgear transformers, cooling infrastructure such as input power to chillers, cry units, AHUs, and some of the more miscellaneous systems such as lighting. Whereas the IT equipment energy purely focus on the IT load, so compute, storage, and network equipment. Partial PUE is fundamentally the same as the above, but it considers the components within a defined boundary rather than the entire facility. And I can explain that in a little bit more on the following slide. So, as an example, PUE, on the slide that's in front of you now, you can see we have a transformer, a chiller, a UPS, and the IT equipment identified, so the IT load. The PUE considers Zone A, everything that you can see on that graphic. So, for example, going into the transformer, you can see we have 600 megawatt hours, and if you look at the example calculation, the first figure is 600. Then going down to the IT equipment level, we have 475 megawatt hours. So it's fairly straightforward to see that PUE for this facility would be 1.26. Moving on to the next slide, this highlights how partial PUE differs from PUE. So if we take partial PUE1 or zone B as the first example, you can see we've got 1700 megawatt hours divided by 1500 megawatt hours. The 17 comprises of the IT load plus the absorbed power of the chiller, totaling 1700 megawatt hours. This equates to a partial PUE of 1.13. Partial PUE2, being zone C, shows 700 divided by 500 equaling the 1.4 PUE. The 700 being the IT load again, plus the 200 megawatt hours indicated in brackets of the chiller. This equates to 1.4 PUE. Now, if we look at the overall facility as a whole, going back to zone A again, we have a PUE of 1.35. So you can see there's depending on how PUE and partial PUEs are reported, there can be some significant differences in the outcomes. So moving on to the next slide, we look at how PUE is measured within the data center. And there are 3 defined levels of PUE measurement, being a basic, intermediate and advanced level. These respective levels consider the IT energy measurement point, the total facility energy measurement point, and the measurement interval or frequency of measurement. You can see PUE1 being the level 1 basic measurement, considers UPS output, measurement at utility input, and on a monthly or weekly frequency. PUE2 considers measurement at the PDU outputs, utility input, and on a daily hourly basis. And PUE3, being more advanced, considers measurement of the IT equipment input, utility input, and 50 minutes or less. So you can see when we get down to PUE3, we're at a far more granular level, and to measure at that level is going to require a more costly infrastructure to support it. So why is measurement of PUE so important? Well, if I compare a PUE of 1.6, which is fairly conservative, against a PUE of 1.15, which is absolutely achievable when best practice is followed, and there are a number of examples of that. If I consider a 2 megawatt data hall operating at around 85% utilization and a power cost of maybe 10 pence per kilowatt hour, that would equate to a power OPEX saving of around £650,000 per annum. Many of the leases that we see and that get entered into are 10 years, 15 years and 20 years. So you can see the importance at £650,000 per annum, the importance of defining PUE correctly and equally measuring it correctly. So moving on to best practices for efficient operation. I mean, fundamentally, this is, so how do we go about optimizing PUE? And each of the subjects shown in the slide is probably a presentation in itself. So I'm going to skim through these fairly quickly, but there is on the next slide a link to a book called Green Tips for Data Centers, which is very, very comprehensive in all of these areas. So starting with the first point, energy management. So the utmost important is to measure performance, and as I've tried to highlight on the previous slide, is provide the infrastructure to enable you to do that. It doesn't matter dramatically whether or not that's you're measuring to a PUE 1 or PUE 2 or PUE 3 standard, but it is important to be able to measure. Plant equipment machinery right sizing. This is probably, from my perspective, the biggest issue with data center operations, and it's very much based on the fact that you're dealing with such high loads, so you end up with very large pieces of plant equipment and machinery, but the actual IT deployment doesn't necessarily, it can be very granular in terms of the build out. So it's important to have plant equipment and machinery that can be matched against that load as it's deployed. Internal environmental conditions. Don mentioned earlier on the recommended and allowable ranges. Those ranges are now being adopted. They're being written into lease agreements now, and people are understanding what that means for them technically and commercially. Airflow management. There are a number of areas here. Many people concentrate on the supply air to the servers and IT equipment, which is very important. But equally as important is to ensure that you've got a good return air path back to the cooling system, whether that be CRA, cracks, or air handling units. Fundamentally important to ensure that hot and cold air streams are separated, and that the right blanking plates and containments installed. And underfloor pressure management is also very important, and that generally means that the below floor structured cabling's managed appropriately. In terms of CRA and crack units in particular, even today there are large quantities of constant volume belt-driven CRA units in operation. Many of them are legacy, but they exist, and there's an excellent opportunity to swap those out with EC fan motors. Cooling plant. I've seen systems recently still put legacy again, but incorporating 3-port control valves to CRA units. There's obviously opportunity to change those to 2-port control and incorporate variable speed pump drives to the chilled water systems. I touched on waste heat opportunities earlier. The waste heat coming back from data centers is generally considered to be low grade, but there are opportunities to reuse it if the IT load does exist. And for example, I'm familiar with data centers with offices associated with those data halls where the waste heat's been used to preheat the fresh air during the winter periods. And there are other examples there of cooling plant, and as I said, there's a lot more detail within the book. Power, UPS efficiency. There's been some great strides over recent years with UPS, and in fact, with the improvements made with the mechanical engineering systems, the focus has really gone back onto the electrical side of things, and transformerless UPS is certainly helping in that respect. Then there's the more miscellaneous systems such as lighting. Now, although that's a fraction of the load within the data center, there are other upsides to energy efficient lighting. And if you think about LED, for example, there are other advantages, not just about the energy efficiency, but in terms of the hours of operation compared to other types of lighting system, and therefore the less frequent need to go into the data hall in the first instance. And then from at an IT level, the virtualization is commonplace now. There are optimization techniques for storage and power management features, and the key there is actually enabling those power management features that are embedded within the IT equipment. Moving on to innovative concepts and solutions briefly before we open up to take some questions. The degree of the applicability of these concepts varies from a project to project basis. Sometimes, for example, direct or indirect outside air can't be achieved within the economic constraints of the development, and the only true solution would be a water-based or chilled water-based solution. But every development needs to be looked at on its own merits. The thermal guidelines for data processing environments, I mean, moving to the allowable range based on giving the X factors due consideration, and the X factor is a baseline failure rate, based on one being the average probability of failure under a constant server inlet temperature of 20 degrees C. Now, the failure rates have been considered by the IT subcommittee within ASHRAE TC 9.9, and those failure rates have been published for between temperatures of 15 degrees C up to 45 degrees C, so that's 59 degrees F to 113 degrees F. And we're certainly seeing a trend where our customers are starting to move more towards that, the application of the allowable range. Compressorless cooling solutions are becoming more commonplace, fundamentally driven by moving towards supply air control and the adoption of the recommended and allowable ranges. We've seen within certain areas of Europe in particular, we don't even enter into the allowable range with the right supply air control strategy, and that's without that's with compressorless cooling solutions. One of the obvious benefits there is not just the OPEX savings that are associated with it, but also the CAPEX savings with respect to the downsized electrical infrastructure. The application of indirect outside air has certainly gained traction with some evaporative cooling. We're seeing high performance computing become more prevalent, I wouldn't say it's mainstream at the moment, but Don mentioned earlier of loads up to 60 kilowatts per cabinet. That will require a slightly different way of thinking with respect to cooling those type of applications, and there are bleeding edge solutions out there at the moment, including full oil immersion solutions through to processor heat sink cooling solutions to more commercially available close coupled heat exchangers, rear door heat exchangers and such like. Decentralized UPS is a proposal that is often considered, and finer granularity in terms of IT deployment on a row by row basis, and probably fairly obviously minimize the number of end-to-end voltage transitions. So I mentioned earlier on about the transformerless UPS technology and PDUs perhaps without transformers.
Paul, how are you doing in terms of your slides there? I can't see.
I think we're there, Tim.
Okay. Well, perfect timing. Thank you very much. Great. We could perhaps leave the further reading sitting there. That would be great, unless you've got a question slide. It's just to remind people, the whole webinar will be recorded and will be available, technology permission, of course, on CIBSEASHRAE.org, as well as a PDF, which will definitely be there if you want to review the slides. Paul and Don, I've got lots of questions coming in, so if I can ask some questions, and if you're able to give reasonably concise answers. We've only got 10 or 15 minutes at most left, so let's. Can I go for one very briefly on some clarification first? And the clarification is there's a few terms that you use there. And I'll just give those very briefly. The four that came up are virtualization, CRAH, C-R-A-H, and CCUs. Can you very briefly just tell the audience what you mean by those?
Paul, you want to take that one?
Yeah, sure. And I apologise for not explaining that during the presentation. So CRAH would be computer room air handling unit.
Great.
I'm just going back through my slides now to see where I.
CRAC.
Computer room air conditioning unit.
CCU.
Close control unit.
And finally, virtualization.
I'll let Don take virtualization.
It converts a physical thing to a virtual thing. So a computer, by adding software to it, a computer can become 2 virtual servers rather than 1, or 3 or 4, or any amount. It's all controlled by software. So it's not a physical server, but rather a virtual server.
Excellent. Thank you. That's really very useful. That was answering particularly Phil. Phil, he's in London. He put that question forward. Now going to a question for Eugene. Eugene asks, now Eugene's in early riser. He's at 5 o'clock in Sydney, so nice for him to join in. 5 o'clock in the morning, that is. And Eugene asks, he wants a little bit of interpretation of the recommended ASHRAE temperature range, the rate of change of 5 degrees C per hour. He sees it as it's caused certain problems because if you take it over an hour, 5 degrees C, that's no problem. But if viewed as a rate of change, you know, a continuous rate of change, it becomes problematic because only a small change over a few minutes could exceed a rate of change of 5 degrees C per hour. That could be a bit technical, I don't know, but what opinion have you got on that? And is there a way out of that, Don and Paul?
Our updated standards that'll be coming out shortly are going to be defining it in a 15-minute period rather than an hour. The available information at the time when we published was for an hour. We had two different numbers, 5 degrees C and 9 degrees C, depending on whether it was a tape drive or anything else. But we have new data that we'll be publishing this quarter.
Okay, so that's hot off the press. And will that be?
Yes.
Will that be in terms of a revised standard, or will that be information that people can get hold of without buying the standard?
It will probably be available both ways. It will definitely be available in the book, and it will probably be available through initially through a white paper on the TC 9.9 website.
Excellent. Thank you very much. That's really good. Now, this question could give us a seminar in itself, but anyway, let's go for it. This one's from Joshua, and Joshua asks, can you explain the various airflow management strategies in practice? Well, perhaps it's a matter of referring people to a book like the CIBSE Knowledge Series book, the introductory book, which is freely downloadable for all CIBSE members, of course, or other references, but over to you.
Paul, you want to take that one, or you want me to take it?
No, I mean, airflow management is so important when we move into the recommended and in particular the allowable ranges. The one thing we want to ensure is that we don't get recirculation between the hot aisle and the cold aisle, because it will impact on server reliability. There are various methods. There's hot aisle containment, there's cold aisle containment, there's chimney systems. There is an endless list, but fundamentally it's to ensure that the right supply air is getting to the server inlet without short-circuiting and mixing.
Right, and so we were negligent, and I was negligent not describing that the room temperature does not matter at all. All that matters is the air inlet temperature to the server. Nothing else matters. And so what's going on with all these different kinds of coupling systems is saying the room temperature doesn't matter, so want a closed couple, almost like you'd think about in terms of spot cooling. So want to have cooling for the IT equipment and want to try to eliminate any other influences. So there's different kinds of mechanisms to do that. Tim, next question.
Okay, thanks for that. That's great. I'll join a couple of questions together here. These are both from the UK. This one from Anthony. He's saying about direct evaporative cooling retrofits for data centers for fresh air. Let's just stick with that. Have you seen successful direct evaporative cooling retrofits to data centers? Now, I saw some of these in Chicago when I visited recently, but Don, you may well have seen some of these, or Paul, some retrofits of direct evaporative cooling.
Go ahead, Paul.
Yeah, I mean, we personally, I've seen direct outside air used in various areas around the world. The solution is very geographic specific, but we've seen successful deployments of direct outside air. My preference is indirect outside air, which is probably a newer solution to the market. It certainly helps cut down issues with humidity control, which can be quite challenging with direct outside air. But I've seen successful applications, and when again it's how it's applied. If you're working within the ASHRAE allowable range, then obviously your control tolerances are far wider, so your humidity levels can go from 20% to 80%. But yeah, so yes, I've seen successful applications. I have a preference for indirect outside air for various other reasons.
And these are
And
in
so
retrofit. In retrofits, have these been in Paul and or Don? Do you about to speak there? Have you seen these in retrofits?
yes, yes, and direct evaporative as well.
Okay, just in case people are unsure, I don't think you covered it in your slides. I was looking at other things, trying to get my connection working here. But evaporative cooling, for those that don't know, is really just a matter of spraying water into the air, and then the evaporating of that water reduces the dry bulb temperature of the air coming into the data center. But of course, by doing that, you increase the air absolute humidity. So there are prices to pay. Right, so you've seen it and it's possible, so that's great. Thanks for that. We've got a couple of minutes left. Let's just pick up a couple more questions. Yes, the other question which is looking at heat recovery from data center using heat pumps. Have you seen any of it? Does this exist? Do people use the heat by heat pumps? This is a question from again Phil in London. Data center heat pumps.
The heat off of the servers, for the most part, is a low-grade heat. And so when you look at the transport factor, typically it hasn't worked out well. If you have a load that's really close enough where you can take advantage of it, then it's a possibility. And on the heat pump, like a geothermal or something along those lines, most of the data centers, because they're running 24/7, the ground starts to gain in temperature because of the load and because it is 24/7. So it works in some cases, but it's a limited application.
Okay. And I would just add to that, Tim, by saying it's sometimes unwise to assume the load will be there. I've worked on a number of data centers now where the projected IT load hasn't actually manifested itself. And then if you're relying on that waste heat to drive a solution, and it doesn't appear, then it can cause other problems, obviously.
Okay, thanks for that. Just to show how international we are, this one's from Romania, and this is from Vasil, and the question is, how do you actually model hot flow from racks and the cold air inserted in the hall? What sort of systems do you use to produce your modelings of installed systems?
Paul, you want to take it?
Yeah, sure. We put a very large investment into computational fluid dynamics. We model the halls both internally and also externally with prevailing winds. And when we're using evaporative systems, we actually look at the moisture diffusion as well in the external environment. But we use, I won't mention any names, but we use what we consider to be the best CFD software on the market, and our consultants do a very diligent job in modelling that for us. But
Paul, since we're short time, let me just quick weigh in and say that the CFD programs, they're generic ones that model the outdoor climate and a lot of different things, but they're CFD programs like what Paul's talking about. They're specifically designed for modeling data centers, and therefore there's less effort associated with modeling through those kinds of programs.
Okay. Well, thanks for that, both of you. That's good information. Let's just pick up one more question. We like to finish it. It's promptly 1 hour afterwards. Let's just go for one more. We got them flooding in here. Let's pick up on this one. The cooling strategy trends. I think there's a lot of technologies that are being used in data centers, and I think this particular questioner, Raphael, wanted to know how does in-row compare in column, crack DX versus crack direct expansion versus crack chilled water, compare, and chiller versus economize. I mean, there's lots of systems, lots of ways this can be done. Where can people go to get this information? We're not going to cover it in 30 seconds. Where can they go?
I'll take that question. Basically, because of that FF&E, the fixtures, furnishings, and equipment, and the occupants being the software, the different types of buildings there are in the world is dwarfed by the different types of data centers there are in the world. So it's across the full gamut. So anytime you try to go ahead and stereotype or say which one's better, this one or that one, there are way too many variables. So you have to look at it on a case-by-case basis. It could be something that's really compelling for one project and totally different for another. Just like a church, a really large church, cooling it is totally different than a little church in the country. So we've got every kind of size you can imagine. We've got every kind of use you can imagine. Like a data center that services the Olympics or things along those lines with tremendous transient loads or ones where it's just a regular, steady as they go kind of load. So it really varies all over the place.
Okay.
And so our books have that covered pretty well, the combination of the books. For example, book number 7 there is the high-density data centers, and that shows overhead cooling. It shows the in-row cooling. It shows in-floor cooling, a lot of different types of methods that are actual case studies, the ones that are in operation.
Thank you, Don. That's great. On a cut in there because we're over time, and just really, I must make sure that people know about as well as the ASHRAE books that we're seeing on the screen there, which are really the international guides. There's also a very much introductory book, the Knowledge Series 18 from CIBSE. If you're a CIBSE member, it's absolutely free. You can go on the CIBSE website and download it. It's a very, very good application introduction, and in actual fact, it's going to be revised fairly soon, I think, and I think Don's actually involved in that as well. So we'll see some interesting changes there, no doubt. Well, I'd like to thank you both. What a fantastic session. This is, in such a short time, you've covered such a vast area, and I think even if it's just whetted an appetite or two, or helped just introduce the subject to the audience, it's been a real success. So thank you very much for taking the time to produce the slides and to present tonight, both Don and Paul, and of course thank you to our audience from around the world. Really great to have you online.